Yeah. Unlike the two previous presentation, I don't have any math formula as far as I remember in my slides. So this will be more still on ZK, but a little bit more on the application side. So with a pun, which is optimistic, I put that in quotation marks. You will understand why in a bit. So we're gonna talk about on-chain AI, and in particular how to bring really large models that we're actually using in Web2 today on-chain. So this is the agenda. We'll talk about verifiable machine learning or AI, and then a little bit about ZKML just for context. And then we'll introduce something that Aura has invented called OPML, standing for Optimistic Machine Learning. And then going into today's main topic, which is a paradigm or a scheme that we call OPI. I'll explain that a little bit as well. I know that's a lot of abbreviations. And then we'll talk about how actually like all these schemes or ideas, how does that actually bring AI and crypto together? Right, so at Aura, first of all, we believe that verifiability is a spectrum. So usually when people say verifiable machine learning, they're only referring to ZK, right? It's true, ZK is definitely sort of the end game of verifiability, right? The most trustless way of having verifiability. But we also think that you can have a spectrum with different security guarantee, right? So we have ZK rollup and OP rollup. Why can't we have OPML and ZKML? So on one side of the spectrum, we have ZKML, which is zero knowledge machine learning. And then on the other end of the spectrum, we have optimistic machine learning, which is, if you understand like OP rollup, it's the exact same thing, right? So we are trusting the system optimistically or trusting whatever results being submitted optimistically until someone challenges the result. And then in between, unlike rollup, which is either OP or ZK, well, nowadays they're also exploring ZK fraud proof. But unlike a rollup where you can usually only use one system to do so, in machine learning, there's actually space for a hybrid of both. Right? So this is where we're standing in between, which is today's topic, optimistic privacy-preserving AI. So a little bit background on ZKML. So how many of you would say that you know what ZKML is? Okay, so ZK, guess, okay, and ML. Okay, great. So ZKML literally means putting a machine learning inference in particular. So we're not talking about like actual learning or training a model yet. We're just talking about making a prediction with a model. So putting it into either a ZK circuit or running it in ZK VM. Okay, so the purpose of it, usually when people refer to ZKML, there's three purposes, which is, of course, first for verifiability. We have a whole slide of that before. But then there's also sort of two promises that I've put with an asterisk. And you would know very soon why there's an asterisk. So usually people say that, hey, ZKML, you not only gain verifiability, but you also have two promises, which is input privacy and model privacy. Right? So you can either choose to keep the input that you put into the model private because of zero knowledge proof, or you can choose also to put the model weights that goes into the model private. And before we talk about why I put those in asterisk, even with with all these promises, so we have problems, right? Which is the same problems that we're facing with zero knowledge proofs nowadays, which is it's super memory consuming, it's time consuming, and hence it's only practical for small neural networks. All right, so to put this into perspective, we're talking about proving something like a GPT-2 or a Llama. It's either gonna take days or it's gonna take terabytes of memory, right? So or both, I guess. So that's why there's a need for alternative. But not only that, not only for all these known issues, actually the two promises that I put in asterisk is also not entirely true. So we'll look into, and this is something that when I was writing the optimistic privacy preserving AI paper, I was doing some simulations, and that's what I found out. Is that, so first of all, input privacy in is tricky with ZKML. It's usually sort of a guarantee when you do zero knowledge proof, right? You put in an input signal, you label it as private, and bada boom, you got a circuit along with the proof that actually seals the input. It's a little bit tricky with machine learning because ultimately machine learning is a program that extracts the statistics of your input. And it's also tricky because when we talk about input privacy, it typically means you distribute the prover to client side, right? So I hand you the prover so that you can generate proof on your device, and you just hand over the proof to me. So that also means that you're handing over the model, essentially. And the problem with handing over the model to client side is that then they get to run inferences over and over and over again for free. And in that sense, they can actually then train a model to inverse compute whatever input you have. So let's say, right, so I can basically generate billions of inputs and then run this through a model, and then using these input-output pairs, trying to compute like an inverse model that will inverse your input. Of course, this is only limited to models that probably don't compress the dimensions as much, right? So of course, like if you have a model that takes a picture and output like a tiny label, right, like an integer label, that's very hard to reconstruct. But there is a lot more other models that actually would not reduce the dimensions as so much, right? And there's a possibility of people reconstructing that. We have actually done that with in the archive paper that will be linked in the link tree later. And so inside there is actually an experiment where we actually try to use ZK, and then right, so we just have like the input and output of a ZK circuit and trying to reconstruct a model that can reconstruct all these inputs. So that's a bummer, right? So okay, well maybe we don't have input privacy always, but certainly we can have model privacy, right? So it actually also suffers from the same problem, which is, again, machine learning is extracting the statistics of these data. And what happened with model privacy is, first of all, you have a limitation that it's a single prover, right? It's a single prover assumption. So, okay, because distributing the model is dangerous, as I mentioned in the previous slide. So, okay, let's take it back. We're gonna do like a single prover assumption, which is whoever holds the model will compute all the proofs, right? Then the model should be secure because only the prover has all the model weights. However, actually, if there is enough inferences that are made in the from this model, right, and you get enough pairs of input and output, you can still then reconstruct or train a so-called like heuristic model that mimic what your model actually does, right? So even then, ZKB doesn't guarantee model privacy automatically. You still have to sort of limit the inferences that is made by your model by either economics or scarcity. So essentially limiting how long you use the same model for. And before people can break your model, then switch to the other model. Right, so the bottom line, what I wanted to show in both the input privacy and the model privacy case is that ZK is a little bit tricky with machine learning, and all this privacy guarantee doesn't come automatically. It still needs to be aligned with economics. And so then, an interesting paradigm comes. Actually, the Aura team encountered this on an ETH research forum post, which is someone proposing something called optimistic machine learning, and he quickly joined the team, and we have been developing this ever since. So optimistic machine learning is the optimistic like roll-up of ZKML. Essentially, we're guaranteeing the security with game theory, right? So you have a submitter, well, you have a bunch of nodes that will compete to be the first to submit a machine learning inference results. And then the other nodes, if they actually want to challenge the result, they can they can initiate a dispute on chain and have an interactive thought proof. So in this case is definitely, I guess, a different trust assumption compared to ZK, which is you only need, well, for ZK it's pretty much trustless. For OP, you need like at least one honest node out of the whole network, right? So the good thing about OPML is you can have huge models. Okay, here's just some example that we have already put on chain, like Stable Diffusion and Llama, but it doesn't limit to that. At one point, we also have Grok, which is like 100 billion parameters on chain. It's just not performant as a model, so we took it down. With ZKML, it's only sort of practical right now with very smaller models, Decision Forest, GPT-2. The experiment we will show later also show that ZKML is capable of doing Llama, but in the timescale of days or hours. But the thing is, well, looking at this graph and also thinking about with privacy in mind, because that's one of the things that people challenge us the most is you lose any privacy, right? As soon as you go OP, as soon as you go optimistic. So hence, then we think of, well, why can't we combine sort of the best of both worlds, right? So we know that with the previous slides, then in ZKML, input privacy might be tricky. Model privacy, maybe, right? We still need to limit the number of inferences that is made by that model. So why don't we think about a way where we can have model privacy, or we need model privacy, but then we also can run optimistically in some of the program. So this is where we introduce OPI. Actually, OPI has a certain meaning in Japanese. So if you're interested, you can always Google what it means in Japanese. But I think this OPI is actually cooler. So it stands for Optimistic Privacy Preserving AI. It's a really cool name for actually a very simple scheme, which is, well, we run OP on some part of the program, and then we run ZK in the rest of the program. Okay, so that's actually the idea. So we're gonna apply ZK selectively, in particular on the valuable parts of a model. Okay, so this is something that is more on the machine learning side. Have everyone heard of like LoRa? Okay, so LoRa is the fine-tuned version of the fine-tuning parts of the Stable Diffusion models, such that it will fit certain style or certain kind of fine-tuned examples. Right, so actually with, for example, LoRa and on Stable Diffusion, so Stable Diffusion is a open source model, right? At least Stable Diffusion 2 is a open source, fully open source model. So really there is no incentive to hide it whatsoever. It can be run perfectly with OPML. But let's say if I fine-tune a model, well, now those fine-tuned weights become valuable to me. And in order to hide those weights, actually, I only need to CKify those weights that are important to me, those weights that have been altered by LoRa. All right, so this is actually the idea of OPI, which is we can apply ZKML selectively, and it's great for fine-tuned models. It turns out that when I was thinking about this idea, I thought Stable Diffusion would be a great example to implement this. Turns out that even if I just apply ZK on the LoRa changed model weights of Stable Diffusion, it's gonna still take hundreds of terabytes of memory. So this is how big machine learning models is we're talking about, especially if we're trying to fit it in ZK. Right, so even if we do it with Stable Diffusion and just on the LoRa weights, it's actually still gonna take a lot of memories and be very time consuming. So we found a better example recently. This is actually not in the preprint, the first version of the preprint, which is actually not a fine-tuned Stable Diffusion, but a fine-tuned Llama. So a fine-tuned Llama 7 billion in particular. And also not LoRa, because LoRa usually means you're gonna change a lot of the weights in the transformer part, which makes like making all the parts ZK very expensive. But then with something called REFT, actually the long term is low REFT, so low rank REFT. You're gonna basically do interventions in these like large language model. And the interventions are actually just a matrix matrix projections. So it's actually very small, And in a Llama 7B Lian model, there is 32 interventions. Combining, they are 2 million parameters. So each of these interventions, and the thing is, each of these so-called interventions can be coded in ZK circuit separately, right? So you're gonna have 32 ZK circuits that essentially you can prove parallelly, verify parallelly, and they are much, much cheaper to prove and verify compared to trying to do the whole Llama 7B end-to-end. So yeah, so this is what we did. I actually just did this like last week. So I did a very naive implementation in Circom with Snark.js and Growth 16, and actually just on my laptop. So on my MacBook Pro with running M3 Max. And here's some result compared to 2 other prover that try to do the whole Llama 7B end-to-end. So the black bars is a recent result from Ligatron. So they did it on a very high memory machine, and they got result which is you need around 10 gigabytes of RAMs in around 14 days, and yeah, right, to prove it. So the time is actually in logarithmic scale on the right side. So and we're talking about, when we're talking about this benchmark, we're talking about proving 1 token. Okay, it's not 1 sentence. It's just a single token. And then there's a more recent paper right after Ligatron has distributed their results called ZK-LLM, I believe from Waterloo. And they used a A100 GPU and was able to do it in 14 hours. Okay? And so then our very naive implementation actually were able to prove it in 2 gigabyte memory. So pretty much any machine that you have on hand, right? Any laptop. And then if we prove it all sequentially, right, just to make the memory benchmark fair. So if you just want 2 gigabytes of RAM, but then you're willing to prove everything sequentially, it takes around 1 minute. And then you can verify everything parallelly in a very short time, because it's a Growth 16 proof with quite with like minimal proof size. So this is the idea of Opai, which is you can think of all these other models that we would love to put in, to have some ZK property, but then it's also more attainable because it's like basically ready for a very large model. Okay, so I'm gonna switch gear a little bit, use the last few minutes to talk about, okay, let's say now, so now we have made proving sort of real life model a reality, or verifiable ML a reality. And usually the questions that we get asked the most in presentation is, well, why do we need AI for blockchain? Why do we need AI on chain? And I would challenge you to think about the flip side of the question, which is actually maybe AI on blockchain is not for us, but for AI. So just to see like how we can use OPML to sort of change some of the paradigm. So actually, when we talk to AI companies, they typically face 2 problems. First of all, of course, their biggest competitor is always OpenAI. No matter what kind of models they do, when OpenAI start doing their types of models, right? For example, text to video, then their whole startup is over. So one of the things that they want to challenge, right, or they want to at least prove to the customer is that, hey, we want to prove to you that we're always using like the same model. We're unlike OpenAI, which they have a slow drift of their GPT performance. We want to show you that there's some verifiability. We are guaranteeing some service that we're giving you. So that's the verifiability. And now, on the other hand, there is another problem, which is, so a lot of startups, they also opt for open sourcing their models, right? So to gain a little bit of more market share for more users to use them. But then when they want to start monetizing it, then it becomes another problem, right? Which is, as soon as it's open source, then it's very hard to monetize. So actually, what we have done is we have basically offer modeled as like a tokenized version of them. So we're gonna take model ownership, which is every model is broken into like tokenization. And then we're gonna pair it up with what we call inference asset, which is inference results that have been done by verifiable machine learning. All right, so you might think, why would that be valuable? Well, prior to having verifiable ML, actually, people would we already have AI art in NFT, right? Like we have always had that. But the problem is no one know what model it has been used. No one even know whether it's an original model from that artist. Maybe the artist just used some random model that they aren't even licensed to use. Right, so actually ERC 707 is the first AI-based ERC that talks about, well, taking either CKML or OPML and let's make this an end-to-end process. So now creatorship of like AI GC NFTs or AI-generated NFTs is an end-to-end process of, hey, I prove to you that I had some input that have put through this model, and here's the output. Right, so now this becomes a valuable piece of data, because that also means that essentially, if someone wants to make, for example, the same inference, they don't actually need to do it again. Right, so this is some sort of it's a piece of asset that will be useful. Right, so yeah, so that's how sort of like Aura has put AI on chain. So I've talked mostly about the first part here, which is like the optimistic machine learning. And to realize optimistic machine learning, we have actually offered like it as a backend of our on-chain AI Oracle. So our on-chain AI Oracle is where developers can call a model inference directly from the smart contract. And then our OPML network would actually supply the results back to the Oracle, and then through like a callback to the user smart contract, right? And then the initial model offering is the other counterpart where we're showing that there's like value from verifiable machine learning through like tokenization. Cool. So that's the end of my presentation. Both the OPML and OPI is actually preprints on arXiv, and it's linked in my link tree.
Do we have any questions in the audience?
Yes. Hey, can you hear me? Okay, cool talk. How do you do verifiable ML if ML is non-deterministic and blockchains are deterministic?
Yeah, that's actually a very good question that we also get a lot. So it's contrary to public belief, machine learning is actually pretty deterministic, or at least can be controlled to be deterministic through a lot of ways. So first of all, if you're talking about the intrinsic randomness of the machine, you can specify a random seed. So that's the first point, but then you still get probably precision errors from like floating point arithmetic. So one way to do so is through software float, which is a feature that you can enable for a lot of targets that is compiled from like Go or Rust or LLVM. And then the second way is actually you can also enable deterministic computation on CUDA. It's gonna add like a 20 to 30% overhead of computation, but it's at least like on the same hardware and the same OS, like assuming everything is the same, but on two like physically different hardwares, you can still do it deterministically. So it's possible. Yeah.
Does that answer your question? Yes. We had one more question. Yes.
Thank you for the talk. I have two questions actually. First, these inference assets that you talked about, are they going to be produced by Aura? And if yes, are you using some crowdsourced GPUs for the task? And the second one is FHE and confidentiality is a big talk right now in Web3 and AI. Do you plan anything in that regard? Thank you.
Right. So with regard to the first question, so we consider Aura to be like a middleware, so hardware agnostic Of course, up to a certain point from like the deterministic perspective, but so we are gonna basically decentralize the node, and for the node, probably then they would be running on decentralized GPU or different cloud services. So that's something that we at least hope to happen. Like we don't wish for all our nodes to be on AWS or GCP. So I hope that answered the first part of your question. The second part of the question is about FHE. I would say we are closely sort of like monitoring and looking at the technology, but we also realize that to have reliable FHE, you also, or at least like trustless FHE, you also first need to do like this ZKify the encryption process, right? So you can't really have FHE without ZK being first viable. So I think that's also the biggest sort of bottleneck that when we're looking at this technology, right? Is first ZK has to be quick before we can do use FHE.
We have time, yes, but we have time for a quick question. So.
Thank you. It was a great presentation. For the optimistic version, does it mean that every time a user wants to make an inference, they send all the information about the inference on-chain? And what's the impact on privacy for that part?
Right. So exactly. So at least for the so for our current implementation, everyone has to send their full input. And the models are actually not any customized models. They are open source models that is like already in our offering. So in short, there's no privacy, and that's why we're exploring. But yes, so but then also even when we're exploring like combining ZK part, it seems like it's easier to protect the model provider more than to protect the input provider because of the limitation of ML.
And that's a wrap. Please, once again, give it up for Kathy.